Hello all, I'm Dr. Gardner at the University of Montana in the Department of Geosciences. And today we're going to be talking about porous media properties and doing a little bit of review on the porous media, get you thinking about the properties and the structure of a porous media. So with all of my lectures, if you really want to learn the material, I highly suggest that you take notes along with me. So if you don't have pen and paper, I suggest you stop the video right now, grab a pen and paper, and then write notes as we go. I'm going to do a lot of drawing and a lot of writing. I'm doing that because I think it'll make you learn a lot more and make a lot more connections in your mind if you do the drawing and the writing along with me. The advantage of a video is you can pause and catch up at any time. So there's no excuse not to do this. You'll develop your own notebook if you do that with good notes about all of these various topics. So let's get started with porous media. Okay, so we're gonna draw a cube of porous media here. So here's our magical cube here. And this cube has a special size that we'll talk about here in a little bit. So cube is of porous media, so it's made up of grains of solid rock that I'm drawing here. These are spherical, but in general, the grains can be of a variety of different shapes. These grains here are fairly uniform in size, but in general, porous media will have varying degrees of sorting and have small grains and big grains, depending upon the depositional environment. And that sorting and the grain size have important control on the properties of the porous media. I'm just going to continue filling out my cube here with sediment grains. And in a perfect world, they wouldn't overlap. I'll try to keep them from doing that. Okay, so this cube has these special dimensions that are generic. I'm going to call it delta Z, delta X, and delta Y. And we're going to call this a representative elementary volume. Representative volume, or an REV. And this size is a special size where a property that we're interested in the porous media. So for example, we'll talk about porosity. This size is enough that we've encompassed enough grains that porosity is smoothly varying from place to place. And there's no one size that is a hard definition of an REV. It's just where the property that we're interested in becomes some kind of meaningful average, and then smoothly varies as we move from one place to another. So this is our representative elementary volume of porous media, and it is composed of sediment grains. In between the sediment grains, we have pore space or pores, all right? Thus the porous media. And these pores are filled in general in hydrology. In general, these pores are filled with any fluid. In hydrology, we're usually going to consider systems in which the pores are filled to some degree with water. So here I'll draw a pore full of water, and I'm just going to sort of continue to link up some pores here full of water. And I'm purposely not going to fill all the pores full of water. All right, so these pores have, or this pore space has some portions of the pores that are full of water. So this is water filled. And the rest of the pore space is air filled. All right, so the porous media, all the pore space is filled with fluid. Some of it is air and some of it is water. All right, so important vocab: sediment grains and the pores. And the pores are these sort of large spaces between grains. So this would be a pore here. And then so these are two pores. And then this area here that connects the pores, this area here, is called a pore throat. And you can think about these kind of like rooms, and then the straws that connect these two rooms, or halls that connect the rooms. So a pore is a room, and a pore throat. That's definitely not how we spell throat. And a pore throat is a connection between these two. All right, so let's just recall some properties of this porous media. And remember, we're talking about a representative elementary volume, which is just big enough so that the property we're interested in has a meaningful average and small enough to vary, I'm going to say roughly smoothly, through space. All right, and I hope that definition is useful for you, but if it's not, I hope it becomes clearer as we continue on in our lecture. Okay, so let's talk about some key properties of this porous media. And the first one we're going to talk about a lot of what we do in subsurface hydrology is basically an accounting of mass or energy in the porous media, mass or fluid energy. So some key properties we're going to discuss right now are properties of the porous media that help us in this accounting. So the first one is porosity. And in this class, I will use the notation N for porosity. And porosity is defined as the volume of voids over the volume of the REV. All right, so if we come back up to our porous media, the porosity visually is the ratio of this area, all right, filled by the voids to the total area of my cube, all right? And essentially, it's a measure of the amount of open space in my cube of porous media. Let's look at the units here. So this is the volume of voids, all right, over the volume of REV. And I will use this notation of V with a slash through it for volume. Just sort of distinguishes volume versus velocity or something like that. All right, so volume of voids over volume of REV. This is a volume is length cubed. So I have a length cubed over length cubed. And so porosity is unitless. All right, it's a dimensionless ratio of volume. Some important relations here with porosity. Well, if I'm interested in the volume of voids, I can rearrange my equation and say the total volume of voids is the porosity times my volume of R times my volume of REV. All right. Another important relationship here is that the volume of the voids plus the volume of the sediments is equal to 1. Is equal to the volume of the representative elementary volume. All right. And I can divide everything by volume of REV, and I will get N plus let's call this V sed over V REV is equal to 1. All right. And that basically says the sort of sediment, the volume of the sediment is equal the opposite of the porosity, V sed over V REV is equal to 1 minus N. All right, so anytime I want to know how much of the REV is taken up by the sediment, I just go 1 minus the porosity. Okay, so porosity, really important to think about how much space is actually available for fluids, how much is taken up by sediments, and just some relationships. And we usually are going to do this using this idea of porosity, which is the ratio of void space to the total volume. All right, so now let's consider the amount of water in an REV. And like I said, a lot of what we do is, account for the amount of mass of water in porous media. And so this is an important relationship. So let's define the volume of water, VW, is the volume of water in our REV. Okay, so we're gonna do a little bit of vocab here. So our saturation ratio, R, all right, our saturation ratio is essentially, well, is the percentage of my void volume that is filled with water. So we define that as the volume of the water divided by the volume of the voids. And that is, again, length squared cubed over length cubed, which is unitless. All right, this is the saturation ratio. And let's think about the minimum and maximum of the saturation ratio. So if I have no water in any of the pores, I'm in Death Valley after no rain for 100 years. All right, no water in any of the pore space, and my volume of water is equal to 0. Doesn't matter what this is divided by. So the minimum my saturation ratio can be is 0. Now take a moment and think to yourself, what is the maximum of the saturation ratio? All right. If I fill all my pore space, again, the only place water can be is in my pore space. So if I fill all of my pore space, then my volume of my water will equal my volume of my voids, and my saturation ratio will equal 1. So saturation ratio, which we often shorten to saturation, varies between 0 and 1. All right. Another way we might measure the degree or the amount of water in our porous media if it's not fully saturated. So when we say fully saturated, we mean that all the pore space is full of water. Our saturation ratio is equal to 1. So if we are interested in the amount of water in our porous media, if we're not fully saturated, we often use the volumetric water content. volumetric water content. All right, and that is defined as the volume of the water in our porous media divided by the volume of the REV. All right, this is again unitless. It's length cubed over length cubed, which is unitless. But now let's think about the max and min of our volumetric water content. All right, so when I'm really, really dry, I have no water volume in my porous media. This is actually really rare, but let's say I've oven dried something. If I have no water in my porous media, my volumetric water content will be 0. But now, let's think about what it is at its max. So take a minute while I write a better 0. And in your mind, decide what the maximum this can be. Well, at full saturation, all right, that means all of my pore space is filled with water, and my volume of my water is equal to the volume of voids, and I get the volume of voids over the volume of REV, and that is the porosity. All right, so volumetric water content varies from 0 to n. When a porous media is fully saturated with water, that means all of its pore space is full of water. It has a saturation ratio of 1 and a volumetric water content of 0. So some relationships that are important here. Well, oftentimes what I'm actually interested in might be the volume of water in the porous media. So my volume of water, I can calculate as the saturation ratio times the porosity times the volume of the RDV. All right. When my saturation ratio is equal to 1, all my porosity is full of water. All right. And so the total volume would be the porosity times the REV. Right? Or the volume of porous media. Saturation ratio allows us to calculate the total volume of water in a sediment sample if we know the saturation ratio. Okay, so now let's think about so this is a way to calculate the volume of water. Oftentimes, we might be interested in thinking about the mass of the water. So this is the volume of water in porous media. So if we want to know mass, well, recall that the density of water is defined as the mass of water divided by the volume of water. All right, and if we just rearrange that, we know we can calculate the mass of water is equal to rho water V water. All right, so if I want to know the mass of water in a porous media, I can just substitute in star for VW. All right, and I will get mass of water is equal to rho water R times N times V. All right, and this now is the mass of water. In our porous media. Okay, so once again, a lot of what we do as subsurface hydrologists is try to think about how much water there is in a piece of porous media or a piece of the subsurface. And this lecture was designed to help you recall thinking about porous media, properties of porous media, and then the space available for water, how we characterize the amount of that space taken up by water, and how we can ultimately calculate the volume of water in an REB, right? We're going to do a lot of stuff with mass balance and conserving mass in a porous media. And so understanding how we move from a volume of water to the mass of water, well, it's just a density term, all right? This lecture was hopefully useful in helping you get your mind back thinking about porous media and the volume and mass budgets of water in porous media. So I hope you enjoy your note taking. Remember to pause and fill out your notes, and I'll see you guys in future lectures.